There we go. Hey there, welcome everybody once again to Astronomy Daily Live. So come on in, everybody. Welcome. Come on into this ever-growing circle of friends where we get together practically every day, and for about an hour or so. It usually goes a little bit longer than that. I really don't pay that much attention, but I like to shoot for about a hour-ish or so, something like that, each and every day, where we get together on sort of this virtual porch. We grab our consumables of choice and sit back, relax, sort of forget about all the other things that are going on and focus on all things astronomy and space and science and all those great things that well, at least for me, I just am absolutely passionate about. So really fun to come in here pretty much every day and shoot the breeze with everyone, see what's going on. I've got an interesting story today, but I'll sort of linger around here for just a couple minutes, make sure that everybody's going to gather in who is gathering in. So it's pretty clear where I am, but the wind is blowing. The wind is blowing like pretty strong. So I don't know exactly what that what that is, what that's about, but it is predicted that the humidity is supposed to spike too. But just before I started this live stream, I went outside, and it was at 29% and steady. So yeah, don't know what's going on there, but so yeah, when the wind is blowing, doesn't matter how clear it is, even if you've got your telescope in a dome and all that, if the wind is blowing too much, you're pretty much not going to be doing things, because just the slightest vibration, right? The wind pushing against the tube of the telescope can jostle it around just enough. And of course, these telescopes, they magnify everything, right? So a little tiny motion here is seen as this big, huge, wobbling thing. So yeah, usually, with most, at least small observatories, and when you put your telescope outside, without some kind of protection, that wind is going to knock you around. And if you're out just looking around and stuff, no problem at all. But if you're doing any kind of photography, or like what I'm doing in terms of doing some scientific work, at least trying to collect that data, to do the science work, the quality has to be very high. And when you've got a telescope rattling around, it's like it's not going to happen. So yeah, that's how it goes. That is the life of the astronomer. So yeah, that's how it goes. So yeah, well, come on in, everybody. Everyone is welcome here, right? Newbies, pros, amateurs, everyone. I would like everyone, to sort of feel as though, they can come in here and just relax and chill a little bit and just have a good time thinking and talking all things astronomy and science and space and all the nerdy things, right? All those nerdy things. I'm working on some new software to make a new kind of data music sound. So hopefully I will have something done with that over the weekend. I'm sort of gonna, I get these things where it's like I am going to do this, and I'm not going to do anything else until I get it done. So that's sort of the mode that I'm in right now with the sound stuff. It's sort of a new thing. Don't know what it's going to look like. Yeah, ERRT. I sort of noticed the little problem that you were having. I think you're probably referring to what was going on your Mixler station this afternoon. So yeah, I'll keep an eye out. I don't see any potential problems. And speaking of co-hosts, Tom, I see you're on the panel. Hey, what's going on over there?
Hey, Cosmic. Not too much. I hope you are well and everyone else is doing okay. For that humidity thing, though, our humidity is probably close to 100% right now. We're expecting 3 to 6 inches of rain or snow overnight. So it will be a white day tomorrow morning when I get up and have to get out the shovel and go to work.
Oh man, yeah. I think I shoveled so much snow. I'm just through with that. I'm just through. I used up my allotment of shoveled snow years and years and years ago. So it's sort of the same thing that happened being bored, right? I just used up all my boredom. So I'm just not bored anymore, and I think I used up all my snow shoveling. So I just don't. At all.
I renew my allotment every year, so this year I haven't used it up yet.
Great. Yeah. Well, that time of year, and if you like that kind of stuff, absolutely. But now I just I sort of like to see it on tops of mountains, and I definitely like to see it on TV. But under my feet, not anymore. Not anymore at all. So yeah. But that is this time of year. I guess there's a big storm blowing through there. So yeah. Yeah, like 3 inches, you said? Is that what they're expecting there?
Well, where I am, it's 3 to 6. A little north of me into Wisconsin, they're talking about maybe more, 6 to 8. And then out east, they're talking about a huge amount.
Well, I'm sure, all the kids are like, man, I hope this lasts. I hope this lasts, because, to have a snowstorm on a Friday night or a Saturday, it's like, oh, you've got all day Saturday and all day Sunday, and what's going to happen on Monday. So yeah, they're probably waiting there, seeing if they're going to get enough, to close all the schools and stuff. So yeah. I remember those days. I went to a private school where you know, all the kids, you know, they'd be coming in from all over the place. So you know, if and when most of the public schools closed, you know, because of snow, which usually happened, you know, if you got more than about 3 or 4 inches of snow, maybe a little bit more than that, excuse me, you know, maybe 4 or 5 or so, you know, the schools would close. That makes sense. Well, not with my school, right? My school, it would have to snow about 10 inches or so to really, you know, close that one down. And you'd think it'd be the opposite, right? You know, kids coming in, you know, from you know, miles and miles and miles away. You'd think that they would close the school more often, but it was actually the opposite of that. But yeah, I definitely remember, you know, the snow days, and those were really, really fun. And in fact, here just a couple of weeks ago, I took a snow day uh, because it snowed here. It snowed here about like 2 or 3 inches or so, maybe two or so, and you know, here it is definitely not safe to drive. You know, I think I would probably be okay, but I'm thinking of all those other people out there who don't have a clue, right? And yeah, I mean, I don't think I've driven in snow in, wow, probably in decades. You know, I've done it in the past, but not recently. Yeah, I think my experience there has dropped enormously. I'm gonna pop back onto the chat here. Yeah. Ron is having some problems with his Mixler station over there. So yeah, I hope that all gets resolved. That's, you know, that's never any fun. You know, these things, right? These kinds of things are supposed to be fun, right? And you know, when somebody, you know, I mean, I don't know exactly what the situation is, right? But you know, it's sort of the rotten apple thing, right? It sort of ruins it, you know, for you know, the whole basket, and you know, that's how the universe works. So yep, it definitely sucks, but hopefully, you know, things will be resolved if that person, you know, deserves to be banned and or, you know, even more than that, you know, because you know, unlike this, Ronald is paying for his service, right? So you know, that sort of, you know, raises the level of all this, because that's essentially theft then. So yeah, well, I hope it gets resolved. So I've got an interesting story. And this is pretty heavy, pretty interesting what happened today. And hello there, kitty cat. So I mentioned a couple of weeks ago that I got a phone call from this lady who was a friend of this other lady who decided this other lady, I don't know how I'm going to distinguish those two. She has lung cancer that's terminal, and for some reason she remembered the fact that, you know, that I was into, you know, the space and astronomy and all of that. And so this lady decided that she wanted to give me her telescope. And so she asked her friend to find me and see if I wanted it. And so, you know, this lady's friend got a hold of me a couple of weeks ago and said, you know, do you want this scope? You know, this lady wants you to have it. And it's like, well, of course, yeah. Yes, absolutely. So a couple days ago, this lady called again, and we made arrangements to meet up so I could grab the scope. And so that meetup was actually this morning. We decided to meet at 9:30 a.m. Right, 9:30 a.m. at a location sort of nearby here. And I actually got the scope, and there it is, right there. It is a Celestron C5. So that's sort of what I was, you know, I don't know why that particular thought popped into my head, but, you know, sort of like, yeah, that's sort of, you know, what I was expecting, because this other lady, you know, she wasn't really, you know, deep into astronomy or anything. You know, she just wanted a telescope, and you know, I'm not exactly sure, you know, what kind of conversations I had with her, but I think I was the one, you know, that sort of recommended this, and you know, made some kind of an impression on her. So let's see, kitty cat. I think you're going to have to move because I'm going to rotate around here. So it comes with this pretty nice tripod here. And that's actually about as low as it goes. And as you can see, the telescope itself actually sits a little bit higher than my C8. And both of those are sort of as low as they can go. So it's got, you know, it's got a pretty good height, which actually makes, you know, the lever arm a little bit more torquey, right? So it's probably going to wiggle a little bit more, but with less weight on the top, that may not be a problem at all. And of course, as you can see, it also has, you know, the Altaz mount there and the little controller on it, you know, the paddle thing. But it came in this case too, which is really cool. I'm gonna open it up here and just sort of show you the inside here. So it's all foam inside there. So, you know, the telescope, of course, would go in here for transport. Now I'm going to put this down so I don't have to keep it on my lap. But it's got a nice big wall wart here. It's 12 volt, 1.5 amp. So that seems to work really well. So I've got that. I've got another cord that looks like it goes into like a car thing. All right, so I can run it off the car if I need to. So that's pretty cool. It's got one eyepiece. That's a 25 millimeter so-called wide angle there, 1.25 inches, of course. What does it say? Model 93007A. So I'll have to look that up. I don't know if that's of any significance or not. So there's that. Of course, all the kiddies like the foam. All right, out of there. I've got I think, pull this out. I think this is, oh, you know what? I didn't even look at this. I thought that this was a Barlow, but I'm looking at it now, and look, it's a Meade. It's a Meade variable polarizing system. I'm gonna have to investigate this a little bit more. Oh, I see. There's a little thing here that you turn, and you can change the polarization. Let's see if we can do this here. Here we go. Yeah, you can see it. Cool. Hey, you know, that could come in handy. That could come in handy. I thought that this was a Barlow lens. I just sort of glanced at it. I didn't actually read it. So, oh, well, that's kind of neat. Yeah, I'm gonna have to try that out and see. Well, that's kind of hard to do. Here, put it way here, right on the lens here. Which I'll line myself up. I'll turn this on. Look at that. Wow. Polarization. It's a beautiful thing. All right. So I'm going to cap that off. I thought that was a Barlow. It is definitely not a Barlow. So I'm going to have to see if I can somehow rig that up with my camera. Interesting. Okay, and lastly, there's a right angle dude that looks like it's missing a piece here. And actually, the lady mentioned that, you know, she didn't know you know, what exactly, you know, to say, you know, but she did indicate, you know, that there was something missing. So I think that's what that is. But I probably am not going to need this. And if I do, I think I can probably get a thing for it. And again, it's that's a Celestron, star diagonal, 1.25 inches. So that's very, very cool. You can see the little mirror in there. Here, I can take, and there's my hand in the little mirror there. Hello. All right, cool. So yeah, pretty neat. This is okay. So this looks, this I just sort of took off of here, and wow, this looks like almost like a thing for an eyepiece without the eyepiece, because look, that slides all the way in there. So yeah, I think that's probably missing an eyepiece too, but that's all right. I have eyepieces for sure. But yeah, I guess I'll probably have to find a thing here, because this part would actually go, you know, right into the bottom of the tube there. The focus on this thing feels really funny. It's kind of hard to describe. On the orange Celestron back there, the focusing knob is like really, really, really smooth. And this one, at first I sort of thought, uh-oh, you know, there's something wrong, because it felt like it was really, really, really loose. But it seems to focus just fine. So yeah, don't know exactly what's going on there. So yeah, so that's pretty interesting, pretty cool that that this lady, you know, remembered me and decided, you know, she wanted to take care of things, you know, before she left, and so, you know, she wanted me to have the scope. Now here's the heavy part, right? Here's the heavy part. So I meet this lady this morning. Like I said, we arranged to meet at 9:30 this morning. And so we did, right? And made the exchange. This lady calls me about 1:30 this afternoon or so. She left a message because I was at work. And it turns out that this lady who had the telescope, right? She had it. You decided to give it to me. I guess she passed away at 9:30 this morning. So that's heavy, you know. That's like, wow, that's really amazing.
It is heavy.
That's pretty heavy. That's pretty heavy. So yeah, I don't know what that means. but yeah, I think that's pretty extraordinary, and yeah. So I'm not exactly sure what I'm going to be doing with this scope yet. I put the webcam on it earlier, you know, just to sort of look through it, you know, and make sure, you know, the focus was good and, you know, all that, you know, but that was during the day, and yeah, you know, I mean, the motors sound good. They seem to move well. You know, the focus works. I looked at, you know, the functionality of the paddle. That all seems okay. So yeah, I mean, it looks like it's a working scope. It's small, right? It's small. But that doesn't really mean very much. Not really, right? So yeah, I think in the short term, I'll try some, you know, some webcam things with the moon and planets maybe, and maybe live stream those. But I think probably where I want to go with this guy is actually get another a smaller camera of some sort. And then go from there, right? I mean, if I can have, definitely, I think if I can have two scopes going at the same time, you know, collecting science data, I think that would be really cool. I don't know, you know, that adds a level of complexity to all of this, but and you know, I really haven't looked to see what kind of mount control, and I'm going to have to get a manual for it too. It didn't come, you know, with a manual or anything, so that should be really easy to find though. You know, those kinds of things are all online these days. But anyway, so yeah, there's the new member of the telescope family there, and yeah, it's sort of you know, it was sort of intense enough, you know, that this lady, you know, one of her dying wishes was for me to have this scope, and you know, she sort of essentially waited until I got it, and then left. So yeah, that's pretty intense. So yeah.
Well, it's very nice of both of those women, to the one to give it to you and the other one to track you down and meet with you and hand it off.
Oh yeah, no, I think that's just extraordinary, right?
Yeah.
I mean, it's extraordinary because you know, she this lady just remembered, you know, my name, and that I had worked at the local store down here, the hardware store, and she came in, pretty often, right? And when people go to a hardware store, they're not there to shop around, right? They have some kind of problem, right? They've got, some kind, not necessarily a crisis or anything, but there were a lot of those. But you don't really go to a hardware store just to sort of browse and look around and stuff. You go to a hardware store because you have a problem, that you want to solve, and most people don't have a clue, right? Plumbing or something, or their lawnmower broke, or whatever it was, right? So I definitely helped all those people, right? But for some reason she, we must have had conversations, about space and astronomy and all that, and so she remembered me, and asked her friend to try to get a hold of me, which she did, and yeah. So I think that is very, very cool, very, very cool. And like I said, I'm not exactly sure what I'm going to do with it yet, but if there's a way, this actually might be a good way, for me to actually enter the 21st century, when it comes, to doing astronomy, and actually get a system that can, track really, really well, do all the guiding, and all of that. So yeah, I think that's pretty inspiring, and I am definitely, regardless, this story is just sort of on top of the fact that yes, this telescope is going to be put to work, for sure. Yeah, no doubt about that at all. And with that story, that really, really inspires me to want to pursue that in a very, very strong way. So yeah, it's sort of nice to have a couple of nice scopes here. It looks like I'm sort of a celestron dude. So but yeah, I'm into good scopes. So the optics for celestrons are very, very good. The mounts are good enough, and with the guiding and all that kind of stuff, they can work really, really, really well. So yeah, I have to see if there's an interface on there, to actually talk to the mount and do computer control. I sort of assume that there is, either through the mount itself, or maybe through the paddle there. The paddle might have some kind of plug-in thing. So yeah, I'll have to look at that a little bit, and like I said, I'll get a hold of the manual and see what the capabilities are. So yeah, very, very cool. Like I said, it doesn't really matter what the size is. There are some amazing things that can be done with anything at all. So as long as long as the aperture is slightly bigger than my eye, and I'm able to take sort of longer exposures, that'll be great. Daniel Browning, nice to see you in the chat. Yeah. It's a good scope. It's a good scope. So yeah, we'll see how all that goes. As I said, at the moment, don't really know, don't have any immediate plans for it, but I definitely want to get it out into the sky, make sure the optics are okay. I checked out the collimation. That looks good. Like I said, I turned it on, moved it around a little bit. That all looks good. I'll do a star line, get it out under the sky, look at some stars. Make sure that the stars are actually little dots. That's always nice. Set one outside permanently. Yeah. A permanent place for these scopes probably wouldn't be a bad idea. That is definitely probably in the plan. I'm not going to do the automated thing though. That kind of thing I've already done, and it's a lot of trouble. It's a lot of trouble. It's actually a little bit easier, to sit there with it and work with it, and that that to me sort of adds a personal touch too. Instead of postage stamp data, right? You sort of get the personal touch. I'll have a maybe not a perfect memory, but I'll know that I was sort of the one that was pushing the buttons to make it all go. So the automated thing is really 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 cool, and I completely understand why people would want to do that, because it's really 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 great to be able to sit here, say in the comfort zone here, and control a telescope that's outside while it's in the cold and everything else. That is very very cool. But like I said, I've sort of done that, so yeah, that can be a lot of effort, to sort of keep that going like that. And sometimes it's a lot easier, just to drag this thing out, set it up, do a skyline, and go, right? So yeah. But I'm going to keep the options open too. So I don't close any doors at all. So who knows? 2 months from now, I could be saying, hey, automated is absolutely great, and I'm going to do it. So who knows? But yeah. All right. Well, cool. I think I need one of these. Cheers. And what I haven't done in a while, I've been sort of really getting lazy about this, and so I'm going to do it tonight for a little while at least. Here is go over to archive.org and see what the latest and greatest research is. I have really really been a slacker with all of that. So let's do that. I'm gonna get myself set up here. I think I already am. Yeah, I already am. So archive.org is, of course, really, really, really awesome. And on it, you can view the latest and greatest research in many different areas, right? And astronomy is just one of them. But definitely my favorite, So so yeah, what I like to do is, well, they post new papers every weekday. Typically like around 1 hour UTC or so. Sometimes it's a little bit later, sometimes it's a little bit sooner, but usually by around 1 hour UTC on weekdays. They will, post 40 or 50 or 60 new papers, all focused on all kinds of astronomical stuff, right? And this is sort of the latest and greatest bleeding edge things that lots of researchers from around the world are working on. Now, of course, by the time it gets to this point, a lot of that work is months old at least. So a lot of these authors, they publish these and then they just sort of move on, right? So they're working on other things when this stuff hits us. So it's sort of new to us, but sort of a little bit old news, to these guys, because they've been working on these projects, collecting the data, doing the analysis, writing the paper, having it go through the process of actually getting it published, and that can take months or years, right? So by the time these papers are actually seen by us, just regular old Joe Publics, a lot of times the authors here have moved on, right? But regardless, here is the latest and greatest. So what I like to do is I like to sort of scan the titles, and if there's anything that sort of strikes me in the title, I'll go to the abstract, where I can get a little bit more detail. The abstract is sort of a like an executive summary of the entire paper. It doesn't have a lot of the details, but it sort of lays out, what they're doing. And so, yeah, in this case, they're looking at, the jets that are being emitted by these active galactic nuclei, these AGNs, and they are noticing that there are magnetic fields, and I dare say that I think in the future, maybe even the near future, we're going to see a lot more of these sort of electrical and magnetic field things coming down, because they whether they're right or wrong, they may be able to explain things a little bit better than sort of our current understanding, which is based gravity, and gravity works really, really well to explain lots and lots and lots of things. But how do you explain these jets that are going hundreds of light years, thousands of light years, right? And they're collimated, right? They're like laser beams, right? How do you explain that with gravity? I don't know. So so yeah, I think sometime in the future, and maybe even the near future, I think the electrical and magnetic effects of things, I think that's gonna raise its head a little bit more. I think that has been ignored for way too long, and I think it needs to be pulled out and looked at a little bit. So, all right, well, enough about that. Let's keep going here. Giant cold satellites from low concentration halos. Stellar population ending, circular polarization to test the composition and dynamics of astrophysical particle accelerators. Here's another one. Yeah, okay, I'm not going to linger on that. Cloud management. Fundamentals of effective cloud management. I guess they mean data cloud. Yeah, okay. I was like, what kind of cloud are they talking about there? But yeah. I hope that we are sort of getting a handle on this huge amount of data that we now have and are soon going to be just completely overwhelmed by. That's a really interesting problem for computer scientists, right? To deal with these large volumes of data, and not only to be able to sort of mine them and extract information from them, but just the simple things like storage and indexing and access, right? That's a it's very, very rapidly turning into an avalanche, and we've seen nothing yet, right? LSST, the Large Synoptic Survey Telescope, is promising at least 1 million transient events every single day. So terabytes and terabytes and terabytes, petabytes of data. So it's just, that's, these things, I mean, back in the 90s, we were starting, to think about, how are we going to handle, these large data sets? So, this isn't a new thing, that somebody's just working on now. It's data management, right? I mean, in general, is sort of one of those really, really cool, computer science problems. There. I don't know. I don't know if there are any other disciplines that handle this volume of data. Maybe the business people, right? The credit card processors and stuff. They probably handle this kind of volume of data. So maybe a lot of these problems have been solved. I don't know. I haven't really kept up on a lot of that, but that's that is definitely going to be sort of an ongoing thing for the foreseeable future, for sure. Let's see, the faintest dwarf galaxies. Cool. Yeah. So I think they just found a couple more of these satellite dwarf galaxies to the Milky Way, where they're talking about 10,000 times the luminosity of the sun. So you can essentially say what, 10,000 stars. So yeah, you know, that's sort of getting into kind of a weird realm, right? Where it's like, you know, I mean, I guess a globular cluster has a particular, you know, morphology to it, and a dwarf galaxy has sort of a different shape and density and all of that. So I guess there still is a way, you know, to distinguish them. But yeah, you know, when you're talking about, you know, tens of thousands of stars, hundreds of thousands, I guess that's 100,000 stars. That's you know, getting to be, at least on a galactic scale, those are pretty small structures. So pretty cool. Extreme lower limit of the galaxy luminosity function. Oldest, most dark matter dominated, as they say. Metal poor, chemically evolved. Unique windows into the formation of the first galaxies. Okay, cool. All right, I'm going to keep going here. A wide orbit exoplanet with a extremely cool name. I don't know. You know, a lot of people don't like these names. I think these names are great. I think they're fantastic. You know, because fundamentally, you know, if you can decipher them, there's actually a lot of information in here, right? 2012, that might be, you know, the year that it was discovered. I'm not exactly sure, but all right, let's keep going here. Eagle simulation, so some kind of model. Ephemeris errors and the gravitational wave signal, harmonic mode coupling, and pulsar timing array searches. Simulating gas inflow. HARPS N. Radio velocities confirm the low densities of Kepler-9 planets. So yeah, you know, they're just looking at the motions of these planets going around other stars. Cool. Uber massive stars. Huh. I don't know if I've ever heard of an uber massive star. Is that a big star or a small star? I don't know. I guess it sounds big.
I think it's big. Yeah.
Yeah. Let's see. Study the solution space of general relativistic axis symmetric equilibria of differentially rotating neutron stars with realistic nuclear equations of state. So all this is modeling, of course, which is fine. You know, that's where a lot of good ideas come from, right? It's like, well, you know, what if we do this? What if we do that? And you know, you can simulate anything, which is great. Lower limits on the maximum rest masses. Can support 2 times the mass of a static star. We call these equilibria ubermassive. In our survey, we find ubermassive stars that can support up to 2.5 times the maximum rest mass that can be supported by a cold, non-rotating star with the same equation of state. Sounds interesting. You know, the theoretical astrophysicists, you know, their imaginations are absolutely limitless, right? Awesome stuff. Yeah, you know, and they get paid to do it too. It's incredible. I love it. So the Radio Galaxy Zoo, cool. signs of accretion in the white dwarf plus brown dwarf binary, NLTT. NLTT, I don't know what NLTT stands for. X-shooter spectra. So of a 0.44 solar mass white dwarf in a short period, is that 101 minute probably, binary system. So yeah, you know, I still, you know, I can't imagine what that actually looks like, right? I mean, if you were there watching this thing, right, you have a white dwarf star, which, you know, is a star that might be, you know, so they say, you know, like the size of the Earth, right? But 1/2 the mass of the sun, right? And then going around it is this brown dwarf companion, which I don't see. I don't see a mass for that brown dwarf in the abstract here, but you know, I mean, it's a, you know, a big, a large object, right? I mean, at least a Jupiter size, probably bigger, right? Zipping around this white dwarf every 101 minutes, right? I mean, that's as long as one of these live streams, right? I can't imagine what that looks like. Anyway, so yeah, you know, they're talking about like an accretion rate. So you know, there's material that is falling, well, going from, you know, the brown dwarf and falling onto the white dwarf. So cool, very cool. They've got a magnetic field here, so 1/2 kilogauss. So that's pretty strong. And I think the average strength of the Earth's magnetic field is about 1/2 a Gauss, right? So this is 1,000 times stronger than the magnetic field of the Earth. So okay, that's kind of cool. Low latency algorithm, multi-messenger astrophysics, predicted correlation between age gradient star formation in fire dwarf galaxies. Fire, feedback in realistic environments. We explored the radial variation of star formation histories in dwarf galaxies simulated with feedback in realistic environment physics. Okay. More theoretical stuff. It's really awesome. Really awesome stuff. But, you know, things, at least for me, it really flies over my head, right? Just way out of reach, way out of reach. And plus, you know, I think, at least in the context of this live stream, yeah, you know, it's really hard to get into theoretical things. Because, you know, I mean, you usually have to do a pretty deep dive just to sort of understand what they're even talking about. So, you know, we're just sort of scanning, you know, these things for fun. So, you know, if there's anything too hard, yeah. But like I always say, you know, I do like to look at the pictures. Look at the pictures of this one, just to sort of see what is going on. That's, you know, that is one of the nice things about models and simulations, is that you can make some really cool looking pictures. So so let's just see here. I'm not even going to try, right? I'm just looking for pictures. Not even going to try. Here's some plots. So stellar mass versus halo mass. Okay, yeah, I'm not quite sure. I'm just, let's see. So this is in units of solar masses, right? So this is going from somewhere around 100,000 solar masses to past 1 billion solar masses. So that's a big spread. And then the mass of the halo, whatever they're calling the halo, is going from what, a little less than 1 billion to over over 100 billion solar masses. So yeah, I don't know how realistic that is. That seems like a lot. There's some, not quite sure what those are. Look back time. Okay. As I said, they can come up with some pretty cool graphics, though, But yeah, I mean, obviously, we'd have to get into this but yeah, well, they've got like air bars and everything on this, it looks like. So that's kind of neat. Lots of wiggly lines. More stuff there. This is a pretty long paper. I mean, I say this all the time, but it always just blows my mind, what we humans are capable of, right? This kind of thinking, and I mean, this takes a serious amount of work. It's just amazing. Just amazing. All right, let's keep moving here. Dissecting the active galactic nucleus in Circinus, a thin, dusty disk and a polar outflow on parsec scales. Again, you've got these collimated things that are just flying, huge distances, right? Ultra diffuse galaxies. It seems to be the faint galaxy and diffuse galaxy day here. Asteroid pairs, a complex picture. We studied 93 asteroid pairs. Wow. Yeah, it's kind of interesting, that we're finding asteroids and comets to be in these pairs, right? Either connected or not. And you don't find them in like 3s or 4s. You find them in 2s or singles, right? But maybe we haven't looked at enough of them yet, so don't know. Kind of interesting though. But yeah, they say a complex picture. I wonder what they mean by that. Both bound and unbound secondaries could be failed asteroid clusters. Yeah, and here again, a lot of astronomers, I think they sort of limit themselves in only thinking about collisions and like accretion, right? And maybe there's other things going on there. I don't know. It just seems a little weird that there's so many of these pairs like that. So, all right, let's keep going here. I don't know. I'd like to see some of these, some pictures. That's a huge author list, by the way. And it looks like it's a big paper, too. Taking a while to upload this thing, or download this thing, whatever you want to call it. Wow, 105 pages. Holy moly. Wow, I guess they didn't write this overnight. And let's see, it looks like the Czech Republic, Slovakia, Ukraine, Uzbekistan, United States, Spain, Georgia, Australia, Israel. Wow, all over the place. What an awesome thing. Korea. What a great thing. This is what I like. This is what I like to see. This kind of cooperation, collaboration with well, lots of representation here, right? Lots of representation.
They got SETI involved in this one.
Where's that?
I saw it in that list you were scrolling.
Oh, here, yeah, right there. Let's see, that's see who's V up here. Oh, it's all mixed up. Let's see, where's our V? V. You see a V? It's got to be a V somewhere. AFW, TUI. I don't see a V in here anywhere. It's got to be here somewhere. I'm just being blind. I could do a search for a small V, but that would be cheating. There's an X and a Y. Where's the V? Huh. A. Okay, I'm going to go through each one of these. A, D, D, F, G, G, H, I, J, J, K, L, M, N, O, B, A, B, B, D, T, P, Q, F, 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 L, M, R, S, T, U, I, A, F, W, G, X, Y, Z, A. I don't see a V in there. Huh. It is a V, right? TUV, WXYZ, and then AAAB. Huh. Unless there's, well, no, I think they're going to list all the authors here. Huh. Well, that's kind of interesting. I don't see any author with a V. So don't exactly understand that. But here, let's just keep going. Don't want to get too hung up on things. But wow, so this is like a book. Holy moly. They should have a table of contents. Wonder if all the figures and pictures and everything. Oh no, there's some. Distribution of past times of close and slow primary secondary clone encounters for one asteroid pair. Wow, okay. Convex shape model of Gickless. Distribution. Okay, so this is sort of a different one. Wow, so they just sort of go through every one of these. Okay. Amazing. But it looks like a lot of these are, you know, shape models, right? So I mean, they most likely, and they probably say this in the paper, these shape models are created by looking at the light curves coming from these asteroids. You know, as they rotate, we see different, you know, parts of the asteroid, and you know, different parts of the asteroid, you know, depending on their shape, what they're made of, all of that is going to reflect light differently, right? You know, so sometimes the asteroid looks a little bit darker, sometimes it looks a little bit lighter, and based on that, you get a pretty good shape model, you know, because usually the rotation isn't simple, right? It's usually, you know, rotating on all three axes. And so, you know, over time, you can get a pretty good idea. They can also use, you know, things like radar, you know, to actually get a picture. But yeah, it sort of looks like they just go through a bunch of shape models here and stuff, which is cool, very cool. But yeah, it just looks like, yeah, in fact, here we go. Here's some light curves. So that's pretty cool. And, you know, these are pretty significant dips, right? These are, I think, R magnitudes, UBVR. So yeah, sort of long wavelength, longish in the red, right? But these dips are, you know, what, 0.2 of a magnitude or so. So that's pretty significant, but they're complicated, right? They're complicated because, like I said, you know, they're rotating in some really, really weird ways. So, but there it is. Yeah, pretty cool. Kind of neat to see light curves, so-called real data, you know. Cool. I'm gonna sneeze. Excuse me. That's what happens when I look at light curves. Some more light curves. Pretty cool. Pretty cool. It looks like you see the solid lines here. Those are probably, you know, they're trying to fit the data, you know, to some kind of a model. And so, you know, it looks like, you know, they have a bunch of models in here, along with, you know, all these observations too, which is cool. Takes a lot of effort, let me tell you, to get this data. That's an insane amount of work. But, you know, go ahead, Tom.
I was just going to say there's a lot of stuff packed into those charts.
Yes. Yes. Crazy amount of work. Crazy. And, you know, I mean, I'm not sure about these models. These models look a little funky to me, but I don't know. Gotta try, you know, and it's extremely easy, you know, to sit here and, you know, sit here on my little chair and be, you know, sort of critical, right? But this is just extraordinary work. You know, even if it's completely wrong, right? Just extraordinary work. Very cool. But yeah, you know, I mean, all asteroids, right, and comets are rotating, right? So we know, because, you know, we've gone to a few of them now. We know that surface features, you know, are complicated, right? And the surfaces of these things are complicated. There's bright spots and dark spots and boulders and all of that. And so, you know, as we watch these things rotate, they're all going to have light curves, all of them. So yeah, you know, this is definitely something, you know, that I'd like to get into. Now, my system will not be able to see a 15th magnitude asteroid. Not a chance, right? But I'll be able to see some of the brighter ones, you know, maybe 12th magnitude and brighter. Yeah, and there's a lot of those. And, you know, the brightness of asteroids sort of depend on a lot of things, right? I mean, it depends on how much light they reflect. It also depends on how big they are, and it also depends on how close they are to us. So you know, and all three of those things, well, I guess their size doesn't, but the apparent size is always changing, and they're rotating. So we're always seeing a changing piece of the asteroid. So all asteroids are going to have light curves for sure. So pretty cool, pretty cool. It sort of looks like they're just sort of doing the same thing over and over again for all 93 of their objects here. There's a nice light curve there. Pretty cool, pretty cool. This model fit looks pretty good. Looks pretty good. Nice. Kind of sparse data there, but they've tried to fit a light curve in there that seems to match the observations pretty well. Another one. And you can see how complicated these things are, right? I mean, it's not just like a sine wave, right? There's all kinds of things going on. So very, very cool. Very cool. Any same kinds of light curves. Yeah, wow. So this might be like a fast rotator, right? It's kind of hard to tell, right? But they seem to be varying in brightness pretty significantly and pretty rapidly, right? I mean, they're not really showing any kind of error bars here in terms of the photometry, but yeah, wow, looks like a fast spinner. Any? Oh, here's some color ones. I don't know what that's all about. Oh, albedos, yeah. So that's the reflectivity. So, right, I mean, there's sort of a distribution here, but at least the mode is the most common one. It's the highest peak one. Look like it's about 0.24, so 24%. Reflectivity, color indices. So this is a color. So this is the V magnitude minus the R magnitude, right? So if V minus R is positive, which in this case it is for all of these, that means that the V magnitude is larger than the R magnitude, which means that it's brighter in R, right? Because the magnitude scale is backwards. So yeah, that's sort of a head twisting thing, right? So V minus R, a positive V minus R means that R is actually brighter. It's brighter in the R than it is in the V. It's a nice head twisting thing. Okay, so here they're comparing the color to the reflectivity. And yeah, there's sort of a bunching up here in terms of the reflectivity, right? Around what, 0.24, right? We saw that in the other graph. It seems to span a lot of different color indices. Okay. They probably have a interesting explanation for that. Let's see, more words. Oh, here comes a serious graph. Oh, I missed it. Poor machine is being thrown to its knees. Okay. Evolutions. Oh, cool. So even the rotations themselves are changing over time. Pretty cool. All right. Well, on these things, that's how it goes. NGC 205. Don't remember. 5 is that that big one? Don't remember now. I think NGC 205 is a really big galaxy. Big looking at least. Come on, Sinbad, where are you? NGC 205. Okay, it's not the one I thought of or had in my head. So no, you know what I was thinking was NGC 253. That one. Oh, M110. Okay. I should have recognized that. 253 is a pretty cool one too. We'll just look at that really quick.
Yeah, you should check the chat when you get a chance.
Okay, yeah, I haven't been doing that. There's NGC 253. Yeah, let me look at the chat really quick. Daniel, well, you know, to collect all that data, yeah, probably what's happened though, right? Probably what's happened is you know, they've just sort of gone back to the archives and sort of pulled all this out. So yeah. Sorry, I need to keep better track of the chat because Daniel's been chatting a little bit. F equals MA. Yep. Cool. Okay. Yeah. Well, most physics is beyond me too. So yeah. Yeah. Uncle Bill, I don't know if we're going to find any WIMPs or not. I think just you know, tickling in the back of my head says that this dark matter, dark energy thing is something else. So don't know. But yeah, it's nice and messy, and I like it that way. All right. Let's see. Check cocoon early spectra, testing emergent gravity. And this is at least one of the ways, you know, that sort of the idea of gravity is sort of moving in that, you know, instead of gravity being a, you know, sort of a fundamental force, it's some kind of an emergent force. It's coming as a result of something else. So that's an interesting idea. Don't know. We'll see. We'll see what happens with that. Early rotational braking. Age determination with eclipsing binaries. That's kind of cool. I'm running way over time. It's always what happens. As you can see, in today's installment, we've got quite a few new papers, and every single one of these, right? I mean, you get into them, and it's absolutely fantastic. So here's active optics in astronomy. That's kind of cool. I'd like to take a look at that a little bit more. Deformable substrates. Cool. Nice. Adaptive optics is a lot to do with mechanical engineering and structural engineering and how solids behave and all that. It's great stuff. Awesome stuff. New models of Jupiter in the context of Juno and Galileo. Huh. So observations of gravity field by Juno have revealed surprisingly small values for the high order gravitational moments. Recent equations of state for hydrogen and helium, much denser in the M-bar region, worsen the conflict between these. In order to circumvent this puzzle, or model studies either ignore the constraint from Galileo or invoke an ad hoc modification of the equations of state. You guys have to be careful. Don't just be throwing stuff in because it seems to work. So apparently they've found some models that actually work with both the Juno data and the Galileo data. Structure must encompass at least 4 different regions: an outer convective envelope, a region of compositional entropy change. I don't know what exactly that means. An inner convective envelope and an extended diluted core enriched in heavy elements, and potentially a central compact core. Cool. That's pretty cool. Pretty interesting. Pretty interesting. Yeah, the Juno spacecraft is wow, everybody's mind. I mean, just the pictures themselves are really great, right? But I mean, that spacecraft is packed with all kinds of instrumentation, magnetometers, things measuring gravitational forces, looking at dust and plasma and all over the place. Good stuff. Solar chromosphere. High velocity string of knots in the outburst of the planetary nebula HB4. All right, I really should probably end this live stream, but I'd like to take a look at that, and then we'll call it here, because definitely respect everybody's time, and I don't like to go too long because this is a daily thing, right? And so there's absolutely no sense in going really long, because if there's anything that we really want to look at, we can always look at it tomorrow or the next day or the day after that. But I'd sort of like to see a picture of this. So they actually went over to MAST and they grabbed images from the Hubble Space Telescope from 1996, right? So this is 22-year-old data. Cool. Let's see some of it. Where is it? So outflows as jets, outflows as knots. There it is. Oh, pretty complicated for sure. Got this weird thing out here. Look at that. Nice.
Looks like sunspots.
Yeah, it sort of does. At first glance, you're exactly right. You know, this sort of looks like the convective cells. And then, yeah, it really does. Interesting. Of course, you know, I mean, what this really is back here is likely, you know, just like, you know, detector noise, right? So you know, they've taken pixels and sort of smooth things over. Uh-oh, I got a doggy alarm. That must mean it's time to go. All right. A bunch of pictures and stuff. Very cool. See, they've got some models here trying to explain the geometry, what they're seeing. Cool. Very cool. All right. I'm really running really long, so I think we should hold off. Like I say, I mean, I could do this all day and all night, but there's always tomorrow. At least there usually is. You know, that's been my experience so far. So all right, I'm going to get out of here for now. Let me check the chat one more time, really quick. And yeah, Daniel, pick away. I don't know that you're going to find very much, but you can definitely do that. So you know, I'll tell you what I know, but I am not going to claim to have any kind of answers or any kind of you know, deep knowledge or anything like that. You know, I'm pretty much, you know, as lost and confused as everyone is, whether they admit it or not. You know, scientists, they're sometimes held to these really high levels where, you know, they're supposed to have the answers, and nobody has the answers. Nobody does. Now, there's a lot of people who have some pretty good guesses and some pretty good stories, and you know, the best story wins, right? So you know, that's fine, but pick away. I will do my best, but yeah, you know, if you're coming on to the live stream, you know, to get some kind of answers or something, yeah, I can't make any kind of promise there at all. So I'm just here, you know, to share the passion and sort of share my journey with all of you, and you know, we're looking at these things together. I don't really, you know, plan any of this or anything. So you know, there's nothing prepared. Yeah, I'm just winging it. This is how, you know, I sort of like to spend the evenings here, and so, you know, I'm just sharing it with you. That's all. And I think it's a lot of fun. So, all right, very cool. I'm going to get out of here for now. So thanks everybody again for coming in. So tomorrow there will be a live stream, but the day after, the day of or the night of the lunar eclipse, the 21st of January, I'm not going to live stream because either it's going to be clear here and I'm going to be outside looking at things, and I think that it would probably do you better to you know, either be outside watching the lunar eclipse, or going online and watching it there, and, you know, sharing in the community there. So if it's clear here, I'm going to take advantage of a very rare dark full moon evening and collect some data, right? And that's in terms of excitement and, you know, what should be really interesting to watch. you should be watching the lunar eclipse. You should not be watching me live streaming trying to find little stars. So yeah. So the live stream for the 21st canceled. Go outside, take a look at this thing, or go online and watch it. There's going to be a lot of live streams of this thing, so you shouldn't have any problem at all finding 1 or 2 or 3 or 10, and have a good time with that. You know, lunar eclipses, they happen, you know, twice a year. And, you know, you sort of have a 50-50 chance of seeing one each time. So you know, they're not rare, but they are very, very cool to see. Very, very cool. And you know, it's really, really cool to you know, confirm, right, that the shadow of the Earth is an actual round thing, right? I mean, it's not an edge or anything like that, right? It's an actual round thing. That's sort of comforting, I guess. So, all right, everybody, I'm going to get out of here for now. So take care. I will see you in a little less than 23 hours from now. All right. Take care, everybody. See you later. Bye.